We often talk about artificial intelligence as if it were a digital ghost, a weightless intelligence existing only in code. But every line of that code runs on physical hardware, heavy, power-hungry server racks that fill massive, temperature-controlled data centers. Training and operating these models require immense arrays of specialized microchips, supported by high-capacity battery systems to manage the intense energy loads. Those components rely on a short list of specific elements: cobalt, nickel, and gallium. These are the critical minerals that form the physical foundation of the tech industry. Because AI cannot exist without this hardware, the stability of the supply chain for these minerals has become a primary strategic concern. Currently, that foundation is built on a terrestrial supply chain, controlled almost entirely by a single geopolitical rival. This chart shows the geographic concentration of the battery supply chain. China dominates material processing for lithium, nickel, and cobalt, and controls nearly all production of essential cell components. This downstream choke point was felt when China restricted exports of gallium and germanium for semiconductors. For the US and its allies, a disruption in these terrestrial markets could effectively halt the production of the hardware needed for the next generation of computing. To bypass this reliance, nations are looking past sovereign borders toward a massive, untapped frontier. The search for these materials has moved to the abyssal plain, 4,000 meters below the surface. Resting on this remote seafloor are millions of dark, potato-sized rocks known as polymetallic nodules. Inside each rock is a dense blend of nickel, cobalt, copper, and manganese, the exact elements needed to manufacture high-capacity batteries. The total volume of these minerals on the seafloor is estimated to be several times greater than all known reserves found on land. For countries currently locked out of terrestrial supply chains, these nodules represent a potential path toward mineral independence. But harvesting these rocks from the deep ocean floor is a massive engineering challenge. Mining firms are testing robotic deep-sea crawlers that use tank treads to traverse the seafloor, pumping the nodules miles up to a surface ship. An intense scramble for territory is already underway, as Western startups and Chinese state-backed firms move to secure exploration tracks across the Pacific. At the center of this is the International Seabed Authority, an obscure UN body tasked with regulating an industry that is already accelerating. The drive for AI hardware is currently moving much faster than our scientific understanding of the deep ocean environment. But beneath the geopolitics lies a stark biological reality. The abyssal plain is a highly specialized ecosystem, home to fragile life forms that exist nowhere else on the planet. This environment operates on a glacial timeline. Life grows slowly, and these nodules take millions of years to form. Mining creates massive sediment plumes, underwater dust clouds that can drift for miles, burying the organisms living in the path of the crawler. There is also the noise pollution. Constant industrial vibrations will shatter the silence of an environment that has been quiet for eons. Because the deep ocean takes so long to recover, the damage caused by these machines will be permanent on any human timescale. We are watching the high-speed race for artificial intelligence collide with the ancient, slow-moving world of the deep sea. Superpowers are weighing the permanent destruction of the Earth's last frontier against the immediate risk of a trade bottleneck. The question remains, is the hardware for the AI revolution worth the cost of the abyss?